Hello. A very important class of archaeological artifacts consists of metal artifacts, but this is a very diverse category made up of various metallic alloys and with a wide range of technologies. They're also important because, historically, metals have often served symbolically as a form of wealth. Consequently, studying the distribution of metal artifacts from archaeological sites can sometimes help us understand things like socioeconomic differentiation and inequality. Many archaeologists actually specialize in the study of metal-related technologies that were involved in making these artifacts, a subfield of archaeology called archaeometallurgy. Because this topic is so diverse, and I don't currently have access to facilities that would allow me to demonstrate things like smelting and casting, today's video will only introduce some of the more general aspects of the study of metal artifacts. Metal is such a versatile material that people very quickly found out that they could apply it to a wide range of functions. So the range of archaeological artifacts that are made from metals is really large. They range from piercing and projectile types of things like arrowheads. So here we have an example of a medieval iron arrowhead. So that's an example of a piercing tool. Other examples of that would be javelin heads, certain kinds of swords and daggers. Metal is very good for cutting tools, so even though people were quite familiar with using flint to make cutting tools, they quickly discovered that metal had some advantages in certain situations, including that it was relatively easy to resharpen it. So once it was discovered that you could make sickles out of metal, for example, so here you have an example of, this is only a 19th century sickle, but it's not that different in design from sickles that have been made for thousands of years. From metal, starting with bronze ones. This one's a steel one. So those things, we're used to the idea we're only finding the flint or obsidian or some other kind of stone that's part of a composite tool or weapon. Except in the case of projectile weapons like arrowheads and spearheads, we don't usually think a great deal about what the rest of the tool look like, although we probably should. But some metal objects that you'll find in archaeological sites don't make a lot of sense until you think about what they were probably mounted in. So this piece of metal here has kind of sharp, unusually shaped end on it, and an elongated piece here, and you might not realize what that is, because unless somebody finds these things in a more complete state, and this, because it's only probably 150 years old, we can find what the rest of it looks like. It's actually part of a plane. So this is the knife of a plane, and it would go in something like that into this wooden block, and then this wedge would be used to kind of lock it in place. And this would be used, in this case, it's not it's not a flat plane, it's just to smooth and flatten a piece of wood. This is one that's made for trimming wood, to make things like window trim or door trim or something like that. So it makes kind of a fancy pattern on a piece of wood, and it's slid across like that. So it's important to keep in mind that quite often we find metal artifacts, we're only finding a small part of some larger thing. So another example of that would be this thing. This is made from, at least this part of it's cast iron. This part might be forged iron. And it has kind of a hook on it, and this kind of cylindrical part that's suspended from the hook. And one might wonder, what on earth is this thing? But you have to think about what this was part of, and in many cases you have to pay attention to the archaeological context. So if you were to find a bunch of things that look kind of like this, in association with something that looks, say, like this, this is a little bit more obviously a horse bit, right? So this might help you interpret this, because what this is part of I think it would be probably part of the whiffle tree, which is the contraption at the front of a wagon or a carriage that you'd have a wooden pole through here, and this would be for attaching leather straps and leads and reins and all that kind of stuff to have the wagon pulled by a horse. So you have to think about what else does this go with. And many of the metal artifacts that we found on archaeological sites belong to some kind of hardware category that doesn't function all by itself so much as it does in combination with other things. So a very common type of metal artifact that you'll find on historic sites in places like North America are nails. And there are complicated typologies of nails that help us date the sites that we find the nails in. But nails are very common on these sites because you have to keep in mind that a single house might use 10,000 nails to nail together its structural parts as well as floorboards and roof shingles or something like that. Various kinds of nails would be used in the thousands. It's not a surprise that in the 19th century, nails were sold in barrels because people used a lot of nails. So on a historic site, you're likely to find a lot of nails. But you're also going to find other kinds of hardware, like hinges and handles for furniture and that sort of thing, so the drawer pulls and hinges for boxes and that kind of thing. So, and they'll often be fragmentary, they won't be complete. So a good guide to try to interpret these things is to look in old hardware catalogs in the case of ones from historic periods. But from more ancient periods, quite often they will still be recognizable to us today because their function kind of makes sense. Like a hinge today is not that different from a hinge that was used in the Roman Empire, for example.
Unlike lithic technology, metal technology is not so much a reductive one as one that takes advantage of metal's properties of malleability and ability to be melted. Barbara Ottaway introduced the concept of the archaeometallurgical cycle to describe the processes involved in metallurgy. These involve mining and ore extraction, smelting of the ores, casting and smithing of the metals to produce artifacts, and then later the use and discard or recycling of artifacts and their eventual burial on archaeological sites, where they eventually go back to being part of the Earth's crust. This cycle is in some ways similar to a chaîne opératoire, but differs in other respects. One of the key distinctions between lithic technology and metal technology is that old or worn-out tools can be melted down to make new ones. Archaeometallurgy not only involves analyzing metal artifacts, but also the technologies surrounding them, including such artifacts as blowpipes and tuyere, molds, and crucibles. As this cycle begins with the extraction of ores, archaeologists have expended a lot of time trying to determine the sources of the metals in artifacts. For artifacts that contain significant amounts of lead, lead-isotope analysis can be a very good choice for sourcing. This works because lead ores of different ages have different ratios of the various lead isotopes. This method shows particular promise in the study of early Greek coins. Because silver often occurs in lead ore deposits, they were often mined together and the silver separated from the lead. But the methods that ancient Greeks used to make this separation, called cupellation, was imperfect. So the resulting silver still contained small amounts of lead. When we measure the lead isotopes in silver of known sources, the lead from Sifnos separates out quite nicely on a scatter plot from the lead from Laurion, which was the silver mine closest to Athens. Leads from Thasos fall in between these two groups. When we also measure the lead isotopes in ancient Greek silver coins, we can match them up to these fields. Not surprisingly, most Athenian coins and some of the ones from Corinth fall within the Laurion group, and coins from Thasos fall within the Thasos group. But the city-state of Aegina seems to have used more than one source for its silver coins. One problem with this approach is that if coins were made from a mixture of silver from Laurion and Sifnos, they would appear to be from Thasos. That's one reason why this method works better for the earliest Greek coins, when recycling of silver was less prevalent. By the time you get to the Roman Empire, for example, any silver coin could contain silver from so many different sources that this method would not be very helpful. In some parts of the Earth's crust, metals can occur in relatively pure form, in which case they're called native metals. Some of the rocks around Lake Superior in North America, for example, are quite rich in native copper. And more than 3,000 years ago, indigenous people in Michigan and Wisconsin used to exploit this resource. Because native copper is soft and malleable, indigenous people were able to shape it by hammering it on a stone anvil, once they had broken it free from the rock. However, they'd have to anneal it periodically by heating, because hammering hardens the metal, which makes it brittle. This method could be used for making fairly ambitious kinds of artifacts, although large examples like this one from the northwest coast of North America were probably made from imported European copper. With the exception of a few metals, notably gold and platinum, only rarely do metals occur naturally in metallic form, such as this native copper you see here. More commonly, metallic elements are bound up with other elements, like carbon and oxygen, into minerals, which we call ores. To extract useful metals from metal-bearing ores requires smelting. Although smelting involves high temperatures, it is not a matter of melting the metal out of the ore. Instead, smelting is a chemical process. In the example of pit smelting of copper, illustrated here, blowing air through the blowpipes, insulated with clay, provides just enough oxygen for the combustion of the charcoal, but it's incomplete combustion, resulting in the release of carbon monoxide. The mineral in the ore decomposes as oxygen from the ore binds with the carbon monoxide to produce carbon dioxide, which is expelled along with water vapor that results from the oxidation of any hydrogen that's in the ore. Later, the metalsmith can remove small pieces of metallic copper that are left in the crucible at the bottom of the pit. After smelting, a coppersmith can put those small pieces of copper into a crucible and heat it to high temperatures so that it melts, and then pour it into a mold. The mold can be as simple as a shaped depression in sand. Once the copper cools, you have an ingot. Minoan and Mycenaean ingots from the Bronze Age of the Aegean were known as oxide ingots because of their distinctive shape. The protruding corners served as handles, making it easier to move the heavy ingots around. While it's possible to use relatively pure metals for tools and weapons, early metalsmiths soon discovered that there were major advantages to mixing metals together to create what we call alloys. Alloying copper with tin, for example, results in a much harder metal called bronze. Archaeometallurgists use a variety of methods to determine the alloys that ancient metal workers used. One of these is X-ray fluorescence, which allows us to identify many of the elements in a material by their distinctive X-ray energies. The X-ray spectrum you see here, for example, has high peaks at energies associated with lead and tin, and only much lower peaks associated with elements such as copper, iron, and silver. This is consistent with an alloy called pewter. A simple open mold was not much different than the molds used to make ingots, and this was a particularly obvious method for making flat axes, which could be hafted pretty much as is, except for sharpening the edge, or have details added later through engraving. Open molds were suitable for making many flat weapons and tools, including sickles and knives. But they could also be used for making more complex shapes, as long as the shape was such that it could be removed from the mold, or else it was necessary to break open the mold in order to remove the tool or weapon. One way to cast bronzes with very complex shapes is the lost wax method. The artisan molds the shape in wax over a clay core called an investment. Copper or bronze pins, called chaplets, that were inserted in the clay investment protrude through the wax. The artisan then encases the wax model with clay, leaving some wax extension called sprues. Heating the mold melts the wax and allows it to run out through these sprues, while those pins or chaplets maintain the gap between the outer and inner parts of the mold. With the mold upended, the artisan can then pour molten bronze into the mold through the gaps that were left by the sprues, called gates. After the metal cools and hardens, the artisan can break open the mold to reveal the bronze and then finish it by removing any unwanted protrusions of bronze and perhaps polishing the surface. Among the more spectacular early examples of the lost wax method are more than 400 objects found in the Nahal Mishmar hoard. This hoard, found in a remote cave in Israel in 1961, dates to the late Chalcolithic period, sometime earlier than 3500 BC. It contains several axes, more than 200 mace heads, about 100 scepter-like objects, and about 5 crown-like objects. A disadvantage of lost wax casting is that each mold can only be used once. Two-piece molds presented the advantage of being able to make complex shapes while reusing the mold for multiple tools. Axe heads, for example, no longer had to be completely flat and could have fairly complex shapes. A telltale sign of the use of two-part molds is the presence of a seam where the two parts of the mold fit together, or else traces of its removal by scraping, grinding, or polishing. Both two-part molds and the lost wax method could be used to make the fairly complex shapes often demanded for jewelry.
One common way to make metal vessels is by hammering sheet metal. So if you want to make a simple copper bowl, for example, you take a flat sheet of metal and you either have a depression, like a hollow in a block of wood or something like that, or an anvil that's convex, like that. And let's say we're using the convex anvil. So let's pretend my fist is the anvil, and then you use a hammer to hammer the copper on the other side until you gradually curve it into the shape of the bowl. And then you have to trim off the edges and so on. One other thing you have to do when you use hammering to shape things, though, in the case of copper in particular, is you have to anneal it periodically. And what that means is you have to heat it up, because as you hammer the copper, it gets hard and brittle, and then it will break. This method actually allowed coppersmiths to make much more complicated shapes than simple, hemispherical bowls and that sort of thing. They would sometimes get quite ambitious about their work. Here we have 3 examples of copper cooking pots that have been made mostly by hammering. In this case, they made them fairly flat bottom. Now, if you look carefully, you can still see the hammering marks on there, and probably these would have been made by hammering into a hollow in a block of wood or something like that, and would have had extra tools to try to make sure they can get these kind of almost right angles around the edges here, as well as quick sharp angles on the rim. So the rim is made in such a way that it would be good recess for putting a lid or something like that. So it's mostly made by hammering, and both on the inside and the outside on all of these vessels, you can see the traces of hammering. Here you can see it most clearly, but most of what you're seeing there is actually damage from use, so it's also been kind of beat up from use. The indentations from the hammering are much more subtle. They're smaller facets on the copper. And you can also see facets around this nearly right angle edge. It's about a 100-degree angle, I guess. And then in the case of these copper cooking vessels, they had to do a couple of other things. First of all, they attached handles to them, and these handles are made from cast brass, and they're attached with rivets. So rivets are essentially cylinders of, in this case, copper, that go through holes that are drilled through the that they're actually made in the handles and drilled through the copper vessel itself, and you insert those rivets into the hole while they are still hot, and then you hammer them on both sides, and that flattens it on both edges, and then when the copper shrinks as it cools, it makes a very tight joint. So they've done that with this one, and then finally, since it's used for cooking, they lined it with tin. So they took molten tin and swished it around inside there, because if you don't do that, you get copper poisoning if you cook food in a copper pot that's not lined like that. So on these ones, the tin is all worn off over time, so you wouldn't want to eat food that was cooked in these things right now. You'd have to, if you're going to use these things, you'd have to re-tin them. Actually, this one might still have its tin intact. It's a bit hard to tell because of all the blackening in there from cooking residues. These are quite old pots, certainly not prehistoric ones. They're probably 100 to somewhere between 100 and 250 years old, I'm not sure. They're not actually that different in their technology and to some degree their shape from the so-called copper kettles that France exported to the New World to trade with the indigenous people in North America during the early fur trade days. The manufacture of vessels from sheet metal could get considerably more complex than what you saw in the case of those cooking pots. Here, for example, I have two coffee pots from the Middle East. They're probably around 100 years old, but they use pretty much the same technology that was used for the last 500 or 600 years. And believe it or not, these are mostly made by hammering sheet metal. So they're obviously the lid is made separately from the body of the vessel, and the handles are attached later on with rivets. And there's in this case, a cover on the spout that's attached with a little hinge sort of thing, with a pin through it. And the knob at the top is actually screwed on. It's actually probably made on a kind of a lathe and then attached with a screw. But the body of the vessel and even most of the lid of the vessel is actually made by hammering sheet metal. To make a much more complex sheet metal vessel like this one, you would have to invert, you do it with the vessel inverted. Of course, the lids and so on wouldn't be attached at that point, but for the body of the vessel, you would have it upside down over a fairly complex anvil that would have a convex surface on it, or an angled surface. Part of it would be angled probably because you want to get this kind of angle for the base. And it would be on a kind of a post or a column, and you would invert the vessel over top of that, and you'd be hammering on the outside against this anvil in order to form this shape. And you'd have to be rotating this frequently while you're doing that to get it pretty symmetrical. You get the radial symmetry in the vessel. And then when the body is finished, and they do a similar thing to fashion the lid, then there are some details that they would add later on, including using rivets to attach a cast, in this case cast bronze handle, or cast brass handle perhaps, is attached with rivets. And then there's small details on the vessel, which they use with again, having an anvil on the inside and a punch on the outside and a hammer. They basically stamp it with designs on the outside, decorative designs. And then small things like these little birds and so on are attached to this. This is also another piece of sheet metal here, with little birds attached with rivets, and then the sheet metal cover for the spout is attached with pins here. And in this case, the spout even is attached, is actually part of the same sheet metal that the body of the vessel is made from. It's not actually attached on later on. It's not welded on or something like that. It's actually hammered out at the same time. So they would have a fairly complicated shape of anvil that would be kind of a form that this would be fitting over. So they, in a sense, the copper sheet is being kind of folded over that form as they're hammering it. It would take quite a lot of skill to do that. And then here you see exactly the same sort of thing, except it's missing the cover for the spout. And this one's quite small, so you would have to have quite a small anvil on the inside. So they'd have different anvils for different sizes of pots in order to accomplish this. The other thing they used to do, on this one it's missing, but they would cover the handle with strips, narrow strips of metal kind of woven across it. And on this one, it's been damaged, so somebody has wrapped wire around the handle to make it a little bit kind of like an insulator on the handle so you don't burn your fingers. Now this one is missing altogether.
Many of the same hammering techniques used for making bowls can also be used for decorative items, like this moche gold headdress piece from Peru.
In ancient China, they made vessels in a very different manner. In their case, they actually cast the vessels using very complex molds, most of the time made of clay. So they would actually carve kind of a model of the vessel that they wanted and then make a mold from that. And then they would pour molten bronze that contained a significant amount of lead into the molds in order to cast these vessels. And these two vessels are a rectangular and a circular example of what are called ding. I'm probably not pronouncing that exactly correct, but basically these are cooking vessels, very fancy cooking vessels. So they are one of the things that defines a ding is it has either three or four legs on it. Most of the time three, so it's a tripod. I presume that would be in principle so that you could place it over a fire for cooking purposes. Although these really nice ones, I presume, are more for ritual purposes, not likely for daily use because they're very fancy. This one, after it was cast, and when they cast it, they would have to do a little bit of detail work to remove the seams that would exist between the pieces of the mold. There'd be small raised ridges that you'd have to chisel away or something like that. And then they also incised lines on the bronze that they used to inlay other colors of metal. So this one has inlaid of a light colored metal, of a kind of silver colored metal, and a brass colored metal or gold colored metal. Now these are just replicas, so on the real ones these might be silver and gold or something like that, but these are replicas, so that's probably tin and brass or something like that inlaid into this one. This one doesn't have inlay, but it has, as you can see, very fancy molding on it with a person's face on both sides, and some handles here for suspension, and again the four legs. And I think this is also this replica is smaller than the original would have been. And then on the inside it's just in this case, a rectangular basin for cooking something in. And on this one, again, just a usual kind of cookie pot sort of shape on the inside. So these originally would have had casting seams on them, but the seams have been carefully removed. Sometimes you might see some traces of the seams somewhere, like around the legs or something, where they wouldn't expect people would see them.
It took longer for ancient metalsmiths to learn how to smelt iron, and the earliest iron artifacts are actually made from meteoric iron, which would have been rarer than gold, and ancient people may even have appreciated its celestial origins. We can often recognize artifacts made from meteoric iron because of their high nickel content. A well-known example of this is a dagger from Tutankhamun's tomb. Unlike modern iron smelting, most ancient iron smelting involved bloomery iron. This doesn't produce molten iron, but instead produces a spongy mass called a bloom that consists of a mixture of iron and glassy slag. And the blacksmiths have to use repeated hammering to remove the slag and other impurities from the iron. Hammering is also part of the forging process, and not only helps to shape the iron piece, but also allows it to absorb carbon. Alloying the iron with carbon hardens it. Cast iron is made from pig iron, which results from melting iron ore in a blast furnace. Cast iron was a particularly popular material in the 19th century when it was used for everything from stoves and frying pans to children's toys. Cast iron has more than 2% carbon, while steel usually has carbon in a range of 0.5 to 1%. Arguably, the height of steel manufacture is in Japanese swords. Manufacture of these sword blades involves a complicated ritual of heating, folding, and hammering the steel until it has a highly layered structure that gives it great strength and flexibility, not to mention a very sharp edge. One of the methods that archaeometallurgists use to investigate ancient metals is metallography. This involves grinding, polishing, and etching small specimens of the metal, which we can then observe under reflected, plane, or polarized light using a metallurgical microscope, or with other methods, including scanning electron microscopy. This method allows us to identify the crystalline and other structures that occur in the metal, such as the tree-like or dendritic structures that occur in cast bronze, or pearlite structures composed of alternating layers of ferrite and cementite that occur in some cast irons and steels. Some of these structures occur because different components of the metal crystallize at different temperatures as the metal cools. This helps us infer some of the processes that were used in the manufacture of metal tools. From the earliest times of metal's use, its rarity and unusual properties seem to have made it a wealth item. This hoard of rings from Nahal Kana cave in Israel, for example, is made of gold and electrum, an alloy of gold and silver. The rings date to the Chalcolithic period, roughly 4000 BC, and they were interred with the skeletal remains of someone who must have been of very high rank. In the Chalcolithic and early Bronze Ages, even copper and bronze would have been extremely valuable. By sometime in the Iron Age, silver and gold pieces with standardized weights became stamped with a device that turned them into coins. In much of the Old World, from ancient to late medieval times, coins were made by striking a disc of metal between two dies with a hammer. This transferred the designs engraved on the dies onto the disc, making a coin. Only after the Renaissance did more sophisticated methods come into play. So-called milled coins were struck on screw presses, where pressure was applied to the dies using large levers that would rotate on top of the press. This resulted in more regular coins and was used until steam presses replaced the screw presses beginning in the late 18th century. In Eastern Asia, however, the trajectory of coinage was different. Coins were usually cast in molds and were almost always made of copper, bronze, or brass, although transactions with large amounts of money could be made with ingots of silver. Although the earliest Chinese coins came in a variety of unusual shapes, they soon settled down into circular coins with square holes, so that large numbers of coins could be strung on a cord. Japan also eventually took part in this tradition, except that the Japanese favored a wider variety of shapes and made considerable use of silver and gold coins, which were made by stamping irregular, rectangular, or oval pieces of silver or gold, and sometimes painting the gold coins with calligraphy. Along with standardized weights, coins can even give us insights into abstract concepts like mass and value. Here, for example, a histogram of the masses of Athenian coins from the 6th century BC shows several distinct peaks. The highest large peak is at twice the mass of the second highest, which itself is twice the mass of the third highest. The smallest peak is at about 1/5 or 1/6 the mass of the third highest peak. Because we have large amounts of written evidence from ancient Greece, we know that these peaks correspond with the units obol, dram, didram, and tetragram. But the use of histograms like this also allows us to infer such systems among cultures for which we do not have documentary evidence.
I know that was a very general video about metal artifacts because I wasn't able to include some of the kinds of things I would have liked to have done. But I still hope it was helpful to you in helping you understand at least the diverse array of the kinds of research that archaeologists can pursue with metal artifacts. If you'd like to learn more about this topic, you can check out Chapter 13 of my book, The Archaeologist's Laboratory, published by Springer, as well as some of the references cited there. And I'll also make some links to some other videos that actually do demonstrate some of the things that I wasn't able to show you down below. And I would remind you that if you want to get updated when I make new videos, please click on the subscribe button down below. Thank you, and stay safe.